enormous data analysis problems that you need to solve. So what does this look like? Well, there's just kind of a little bit of the algorithm down here for those of you who are computer scientists to give you a sense of what this algorithm looks like. What it does is it takes the reads, the output of the sequencers, which are strings of 4-character alphabet, that are a little bit too short to actually find genes in them, things like that. You actually chop them into smaller pieces. They're called k-mers. That's a fixed length piece, and we're going to hash them. We're going to stick them all into a hash table. So a typical k-mer length might be 51, so we'll hash on these 51 length characters, and then we think of that hash table as a graph, because each one of those hash things that we put in the hash table also has one character to the left and one character to the right that appeared in the read. Assuming that was somewhere in the middle of the read. And then you can use that you can pick up something in the hash table, slide one to the right or one to the left, hash that thing and look it up in the hash table, and in that way do a depth first search on the graph. And that's the basic algorithm that is used to put together these longer pieces. There are a number of other phases in the algorithm that also walk over the graph and put different things inside of the hash table besides just these k-mers. You also put the longer contigs and things like that. So the point of this is a very different workload than the kinds of things we're used to doing in scientific simulations. There's no floating point arithmetic in the entire application. It's all string manipulation. You can call it integers if you want, a lot of logical sorts of operations. There's a little bit of kind of filling in a little matrix when you're trying to do something called alignment. So there's a little optimization inside of there. But a lot of this is manipulating things like graphs and hash tables. So it actually scales quite well in spite of the fact that it's very irregular. This shows the scaling across a number of nodes. Now this is actually still a fairly small data set. This is strong scaling, so a fixed problem size run on multiple nodes. This is a human genome, and we did that because the environmental genomes still are large enough that we have trouble fitting them on any modest number of nodes. These applications also require that you're able to inject lots of messages into the network very quickly, and that you're able to, they would benefit, as we've seen from some initial experiments that are not yet in this data, from things like remote hardware atomic operations. So both of those are things that we think about both in how we program it. Turns out this is written in a language called UPC, which I know some of you are familiar with. If you're not, it is a parallel language that I've been working on for a number of years and allows you to directly read and write memory across the machine, which is very useful in these kinds of data structures. So I think the other thing that we're seeing is simulations of infrastructure, and these kinds of three of these simulations, the power grid, earthquake modeling, and the urban systems modeling are all part of the US Exascale project, the DOE Exascale project. Transportation is another thing that we are working on specifically at Berkeley Lab with some internal funding, looking at scaling that up. What comes up in all of these applications are large amounts of data collection in very distributed kind of Internet of Things ways. You have sensors that are either, in the transportation case, think of Google Maps or something like that. It turns out, and this was something that was a surprise to me, Google Maps is not just reporting observational data. They're actually running simulations, and they're running those simulations in order to make predictions about what the traffic is going to look like by the time you get to a certain location. Now, it's not always perfect, as we know, and they're looking for better simulation models, but they actually do use simulation and prediction in addition to observational data. So you're, in some sense, trying to fit the observation and the simulation together. And the same thing comes up in earthquake simulation. This is looking at trying to do very detailed simulation of the structures that we build, buildings that we build, that are specific to the particular soil that's underneath them. So it turns out that the way earthquake kind of engineering codes work today is there's certain standards that says a building must have a certain structure. And of course, they change over time as we learn more and more about earthquakes. But what we haven't done yet is really tailor those standards to a particular region or particular soil structure that's underneath that building. And so in this project, which is Dave McCallan's project, they're looking at using smart meters that the power company is going to be installing. They're upgrading their smart meters in everybody's homes, which will have little seismometers in them, and they'll collect really fine information about earthquake and other kind of seismic activity, including things like the subway train going by or something else that causes a little bit of vibration, and then you use that to build a model of what the subsurface looks like, which tells you something in more detail than we can by just collecting a few core samples of how that particular area may behave in an earthquake, and use that then to set standards on what the structure of the buildings should look like. Similarly, for the power grid, will be sensors around, and as we get smart grids that are going to be putting more power in dynamically from things like solar power, we need to understand much better the dynamics of the power grid and urban systems, which includes partly transportation, but this project and the Exascale project is focused on looking at buildings and the heat and the kind of heat alleys that come up when you build large urban systems. So in general, these simulations and associated observational data are going to be used for infrastructure planning, to do scenario analysis for things like emergency response, for looking at behavioral analysis, which is kind of a separate simulation problem, but trying to understand how humans behave, because if you're going to look at things like transportation, you need to have humans in the loop. And as we know from things like shopping online, there are pretty good algorithms for making predictions about what humans are going to do in certain situations, such as when you're shopping for something, but we need to apply this to things like use of energy or use of transportation systems. And it can also be used then for policy and economic analysis. So just a common pattern that comes up in these types of problems is combining together observational data and simulation. I talked about that at a high level in the cosmology case. In this case, what we're looking at is putting together, for example, detection data that's collected all around the Earth. This was actually some work done a few years ago by a student at the time, Scott French, at UC Berkeley with his advisor, Barbara Romanowitz. What they were trying to do is understand the deep subsurface structure of the Earth. And they're using sensors from earthquake monitoring all around the world, and they're using that to build a model of what the deep core of the Earth looks like and how that relates then to the things that they're seeing in these earthquake models. So once again, they're running a simulation. The simulation was written in, I think, with Fortran and Scale-a-Pack and things like that, kind of standard tools. But it turns out one problem they had is when they got to the point of trying to kind of put it together and fit it with the observational data was not laid out in any natural way. It kind of came in however it came into the system. And so they had a problem of how to put this big matrix together and compute the errors between the observational data and the simulation so they could make corrections to the simulation. So that part of it they put into they used one of these global address-based kind of models. In this case, it was UPC++, to be able to directly read and write memory on a remote processor. So this allowed them to actually run a much larger simulation than had ever been possible before. Not by rewriting the entire code, but just by rewriting one piece of it. And this is a little bit of performance data and kind of a little graphic that shows you what it looks like to take these submatrices and write them in various patterns that are usually strided. They're not necessarily contiguous in this large shared matrix, which is spread out over many machines. So that gives you some hints about some of the computer science challenges. I know many of you are computer scientists, so hopefully I've given you some sense of how these exascale computers will be used for basic science problems as well as for infrastructure simulations and human health and other kinds of applications like that. But you may be wondering, well, why should I care if I'm a computer scientist? So what computer science breakthroughs will we get from Exascale? And rather than telling you about the breakthroughs, I'm going to tell you a little bit about the challenges that come from for computer scientists trying to reach Exascale. And I'll start with something that I think most people are aware of, which is the end of Moore's law, so the end of transistor density scaling, and the ITRS that has historically at least set the roadmap for chip density has predicted that the end of Moore's law scaling will happen in 2021. Now, we could debate about whether they're right or wrong by a year or a couple of years yet, or whatever, but the point is that we're getting to the end of when these chips when the transistors will get smaller. And that has had a dramatic impact not just on the size of the chips, but actually the speed of the chips, the performance of the chips, and the energy efficiency and the cost. And so it's allowed us to buy more and more computing, exponentially more computing over time for a constant cost. This has very direct implications for exascale or beyond exascale as we look at these systems. And of course, Moore's law is not going to just sort of run full speed and then come to a dead stop in 2021. What we're seeing is it's harder and harder for chip manufacturers to make systems with smaller and smaller transistors in them already today. So things will slow down. But also, as you know, we ended up with multi-core a few years ago because of the end of Dennard scaling, which said that even though you could put more transistors on the chip, you couldn't make the processors any faster because of heat density and related problems. Okay, so what are we going to do about this? Well, we're going to see a couple of things, but I also want to talk about looking at alternative chip technologies because, of course, one of our hopes as computer scientists is that the electrical engineering people will solve this by coming up with a new type of transistor device, although we're getting pretty close to atomic scale in terms of size, but maybe we'll come up with something that's much more energy efficient. This is looking at and it's kind of a cartoon graphic, although the actual data looks similar, for something called TFETs. So the red curve there is today's CMOS technology, and the green curve is a TFET, and this is energy versus performance. So these tunneling FETs or TFETs have an energy advantage, which means we might be able to get more computing per dollar, at least cost of ownership, if we use these kinds of devices rather than using the traditional CMOS technology. The downside is it turns out that advantage, so this kind of crossover point in terms of energy, where the green line is below the red line, is over here on the left of the x-axis. That is where the performance is quite low. So what does that mean? Well, it's kind of like what we saw with multi-core, which is you may be able to get some advantage by using this kind of technology. And by the way, other technologies that people are looking at have similar kind of characteristics at a gross level, which is maybe you can get more energy efficient transistors, but you're going to need, but each one of them is going to clock a little bit slower than the current high-speed transistors that we're used to using. So the trade-off may be we can get more transistors for a constant amount of energy, but we're going to have to have more parallelism because each one of them is going to run a little bit slower. So it's kind of like the multi-core era, but now down at the device level, even more parallelism. So what is the kind of end game, I think, for Moore's law? As we get towards the end of Moore's law, what we're going to see is more specialized architectures. There is no silver bullet that we can see so far in terms of saving us with general purpose devices. And what we're seeing is, for those of us building or thinking about building exascale machines, is a whole set of options: Xeon Phi, ARM, GPU accelerators, other kinds of accelerators, and lots of different options. But we also see kind of in the middle here a trend in industry of going towards specialized architectures, especially for the deep learning market, which is such a large and sort of hot market right now. So NVIDIA is building deep learning application using their P100 Teslas and even more advanced processors. Intel, about a year ago, bought a company called Nirvana, which was building special purpose deep learning architectures for deep learning training. And Google has designed its own tensor processing unit, a TPU, which has its own processor chip for doing deep learning inference. And so what we're seeing is this trend in industry towards specialization that I think we have to think about in the scientific computing or in the HPC community as well, because things are becoming more specialized. And that creates a real software problem for us because we've got millions or billions of lines of code across all the different applications, and we have to figure out what to do in order to target these specialized architectures. Now, as a compiler person, or maybe I would even say former compiler person, I would like to say, oh, well, just wait, and the compiler people will solve this problem for you. There are two hard problems when it comes to optimizing compilers, and especially building automatic parallelizing compilers. And remember, I just told you that we're going to need even more parallelism at a finer level than we have to deal with multi-core and many-core processors. The first problem is dependence analysis is quite hard. And it's especially hard when you use languages with fairly unconstrained pointers in them, such as C or C++, or you have things like the ability to kind of overwrite memory, as you have in certain versions of Fortran. But even with more dynamic languages, such as Python, it becomes quite difficult to do completely static reasoning about the dependencies in the program. The second problem is even if you can do perfect dependence analysis, you may not be able to figure out in the compiler what is the right code to generate because your architectures have gotten so complicated. The pictures down at the bottom are showing something called the roofline model, which looks at a bunch of different algorithmic kernels that come up in science codes, everything from dense matrix multiply, which is that red thing up near the top, to sparse matrix vector multiply, which are the blue blobs down at the bottom. There's 3 of them because it depends on what your sparse matrix looks like, exactly what performance you get. And the roofline kind of tells you what the best possible performance is that depends on how much arithmetic intensity you have. So if you're under this diagonal part of the roofline, you're bandwidth limited. If you're under the flat part, then you're limited by the peak computing performance of the architecture. So what we've learned is that systems may be able to, even though we kind of understand what these graphs look like, it is very hard for a compiler to understand the entire memory architecture of your processor and figure out, even just for a single processor or a single multi-core node, to try to generate the right code for that. And so what we have used is auto-tuning that does a certain amount of search over at least perhaps a constrained set of possible solutions. And what we probably will need to do for the dependence analysis problem is write in more domain-specific languages that have better information about, for example, if you're using matrices or you're using strings or you're using something that, that tells the compiler exactly how you're using it so that it can do better analysis. So we have a number of these domain-specific languages or domain-specific libraries that have been highly optimized using compiler and in some cases auto-tuning technology. On the right-hand side, you see some of these. So these are what we often call the 7 motifs of scientific computing, a phrase coined by Phil Colella. This is so dense linear algebra, you have a library such as Atlas. For spectral algorithms, things like FFTs, you've got FFTW or the spiral library from Carnegie Mellon and elsewhere. Sparse linear algebra, we've done a little bit of work in that area. Structured grids, not clear. And the problem with structured grids is that the structured grid itself is very simple, but the operator that you want to solve on that grid, you're going to walk over that grid and sort of do a relaxation on every point, is completely dependent on the application and the algorithms. And every different application person has many of these different operators in their code. So as a computer scientist, you may say, well, that's fine. We'll just write an optimized structured grid library, and you can hand me a function, which will be the operator. But the problem is that you need that function in order to you need to know exactly what neighboring points you're going to look at in order to do optimizations. So I think, by the way, on the left-hand side was some very rough analysis, so take this with a big grain of salt, that I did a few years ago on the NERSC workload. We asked all the users of the NERSC workload, which of these different kinds of techniques do you use in your application? And they can pick more than one. But what we found is the most popular was structured grids. And even all of those adaptive mesh refinement algorithms I talked about earlier, although they're hierarchical, they're still structured inside them. And so what this means is you really want a very high-speed code generator and optimizer for them. So this says that these kind of stencil operations or structured grid computations are probably the most important next place for us to have impact in computer science, in terms of being able to write highly optimized code generators for this type of workload. A number of people have done this, and one of the examples is a language called Halide, which was actually not developed for scientific computing. It's developed for image analysis. Jonathan Reagan-Kelly did it as a graduate student and is now on the faculty at Berkeley. It's actually being used by Google and by Adobe. So anytime you upload images, which by the way I was doing this morning when I was looking for various images to put in my talk, you upload an image into Google image search or something like that, it will actually use this Halide algorithms to do some analysis on that image. And they also have about 50 people out in industry who are working on this language. So out in industry, they've actually used these domain-specific languages. It turns out that Halide, because of what you want to do on images, which things like convolution, so they also look like sort of nearest neighbor computations on a grid, may be applicable also to scientific problems. And there's some performance numbers, and they run it on GPUs as well as on CPUs, and get the higher numbers are from the optimizations that Halide is doing. We recently worked on a language called Snowflake. The problem with Halide is that it doesn't really handle complex boundaries. What you see in these adaptive mesh refinement codes is a lot of action happens where you have one patch at one level and another patch at another level, and they have to talk to one another, and that causes fairly complex indexing, and therefore very expensive sort of manipulation of the data structures. And there are also physical sort of boundaries that come up in various contexts in the scientific applications, such as if you're simulating, say, the combustion process in an engine, you've got the structure of the engine in the way. So I think there's still a lot of work to be done in more powerful ways of building these domain-specific languages for things like these much more complicated stencil patterns and boundary conditions. So what about algorithms? So I'll just say a little bit about algorithms. And first I'll start with one other observation about the hardware. Which I know many of you know very well, and that is that the most expensive thing that we do on an HPC system, actually on any computer, is move data around. And this shows the cost and time, a number of nanoseconds of moving data around of various years, and so each of these curves are kind of generally coming down, but you can see there's a big gap between moving things around in the CPU, moving them into the cache and SRAM, and moving them out to DRAM, or of course out to disk, which is much more expensive. So in an exascale era, we're really concerned about the energy, though, efficiency of the machines and where the energy is going. And it turns out that energy is also that data movement is also the most expensive thing that we do in these systems from an energy perspective, not just from a time perspective. And so this pyramid looks at the number of picojoules required to move data just across a millimeter of the chip, the cost to move it across 20 millimeters across the chip, and the cost to go off chip. And so you can see you get from the sort of local computation, or sorry, a floating point computation at 100 picojoules, it's still, to move it even to DRAM is another order of magnitude more expensive in terms of energy as well as time. Okay, so what can we do about this from an algorithmic perspective? Well, we can look at better algorithms that actually that minimize the amount of data movement. So at Berkeley, we call these communication avoiding algorithms or communication optimal algorithms. This is actually some work that was done by Edgar Solomonic and Jim Demmel looking at dense matrix multiply running on an HPC systems. This was on Blue Gene P on 16,000 nodes. And this is running time, so down is good. And their algorithm is called a 2.5D algorithm, and I'll give you a little hint about what that looks like in a minute. The original algorithm is what's called a 2D algorithm. So the left side of each one of these sets of bars is the original algorithm, and the right-hand side, the 2.5D, is their optimized algorithm. And the left-hand side, the 2D algorithm, by the way, is what's in libraries such as Scalapack. And so even though we've been working on optimizing dense matrix multiply for probably as long as we've been building supercomputers, there still was actually room for improvement relative to the algorithms that were occurring in these popular libraries. So what's going on here? Well, just at a very high level, I was surprised that matrix multiply, dense matrix multiply even, still had room for improvement. The idea is to make multiple copies of the result matrix. If you're computing C equals A times B, so C is the result matrix. And rather than just dividing up the C matrix in pieces and saying one processor is responsible for computing one piece of the matrix, you actually make copies of it and have a bunch of processors all responsible for the updates in that particular part of the matrix. And it turns out you can also prove that this is optimal in communication, which the original 2D algorithm is not. Kind of the lesson is, in order to make these copies, you do need more memory. So if you've got more fast memory on your system, whether it's cache or you've got more DRAM because you're running an HPC system, you should take advantage of this technique, and you should and not use kind of the traditional owner computes rule that says, I've got a domain, let me just divide it up into pieces and independently have each processor compute each one. So basically what you're doing here is you're going to replicate this data structure, independently compute on it, and then do a reduction on it. And how much replication you'll have depends on how much memory you have. We can also show optimality for that. There are questions about whether compilers could automatically generate this kind of code. I'll just give you a little idea of how this works in, say, an n-body calculation, which is even simpler than matrix multiply. So if we're trying to, this is now just a really naive n-body calculation in order n squared algorithm, we have a list of particles, and we need to interact all the particles with each other. So a common way, if you're a beginning HPC programmer, to do this is to say, well, if I've got P processors, every processor is going to get N over P particles. It turns out that is not the best algorithm. The best algorithm actually makes multiple copies of your particles, at least kind of logically, and it has each kind of row of this group of copies. So C is the number of copies. We divide our processors into these C groups. They're going to be responsible for some set of the updates. So they're going to cycle the particles around. And it turns out that you can prove, and I won't read through all the text here, but you can go back. I'll put the slides online on my webpage a little bit later. In fact, they're almost there. I put the link in. That you can prove that you actually send less data, both in terms of the volume. You send fewer messages, so the number of messages is smaller, and you also send less total data. So you improve both bandwidth and latency by using this, what we call a 1.5D algorithm, because we're dividing it up. Kind of the 0.5 refers to the fact that we divided the processors up in kind of a half dimension, the C dimension, which tends to be fairly small. So this also gives us performance improvements. This is running time once again, and there's the replication factor. So this is for a fixed problem size. So if you don't replicate at all, you spend an enormous amount of time doing communication, and if you do some amount of replication, then you can get much better overall performance. You do have to do a reduction across the different copies, and so this has to account for the reduction time, which you see in the blue piece as well. And this actually shows that we also get very good strong scaling, close to 100% parallel efficiency if you pick the right replication factor. I think I'll skip the symmetric example and just mention that this idea can also be used on sparse dense matrix multiply, where you also have there's a number of different algorithms here that we're looking at. One of my students, Penporn-Koanantakul, did this work. So these are 0.5D algorithms, both 2.5 and 1.5D algorithms for sparse dense matrix multiply, and you can see enormous spread in the execution time here. And exactly which one you want to use does depend on the sparsity of the sparse matrix, of what the pattern looks like, and how large the dense and sparse matrices are relative to one another. So overall, she got about 100x improvement or at least at this particular point. By running on 1,500 cores. So you can see this is also very important when it comes to optimizing, getting a better absolute performance. So, you know, we've spent a lot of time over the years in the HPC community looking at the LinPack benchmark. And I think ultimately the performance that we get, or the success of our Exascale program, is not going to be measured by the speed of the machines or by the speed of the benchmarks, but by the speed of the actual applications and the ability to actually produce real scientific results. But if you look at, and there's a lot of interest right now in machine learning algorithms and data analysis algorithms, it turns out that there's a lot of linear algebra. And I just have a sense, I can't state this as a fact or anything, that we're kind of at the early LinPack days of data analysis, and that deep learning is really dominated by dense linear algebra, of course by narrow data types, narrow, not necessarily 64-bit floating point, and that sparser techniques, just as they did in simulation, may become more and more important in the future. But this is just showing a number of different linear algebra kernels and how they appear in a number of different machine learning algorithms. And certainly dense matrix multiply is over there for deep learning convolutional neural nets, but a lot of other machine learning techniques actually rely on sparse matrices and don't necessarily rely on matrix multiply, but matrix vector multiply, which has much lower arithmetic intensity. So just to summarize, I think exascale computing will absolutely deliver scientific breakthroughs, and those will include breakthroughs in both simulation and in data analysis problems, including machine learning, as well as other kinds of problems such as genomic analysis and graph analytics, but they require advances in the models, the mathematical models that we're using, the simulations, the algorithms that we're using for both analysis and for simulation, and the software techniques that we're using. They will be taking advantage of novel and interesting hardware. There's a huge diversity of approaches already that we're looking at in terms of how to build an exascale machine. But I do think it's also going to impact a broad set of applications that includes fundamental science questions such as cosmology, health examples such as cancer research, manufacturing. I didn't talk about that a lot, actually at all, but it comes up in both actually the genomic problem when you're doing biomanufacturing, but looking at materials modeling and other sorts of manufacturing optimization problems, environmental science, as well as design of infrastructure. And I think there are still a lot of computer science challenges that will happen both between now and the first exascale machines and for many years after that as we deal with the ramifications of the end of Moore's law. So kind of my parting note is it's the end of relaxed programming. This is a recliner chair called the Barker Lounger, which was kind of the epitome of being really relaxed. This was very popular in, I think, the 60s. And so there's our programmer relaxed, sitting there on the Barker Lounger with his feet up, her feet up down below. And I think that's the end of this kind of programming. Instead, programmers are going to have to get really serious about how to get performance out of these machines. Moore's law, you can say, is the law that taught performance programmers to relax. And so the end of the relaxed days are over for them. So thanks very much.